Welcome to Stories from the NNI. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. Today, it's my pleasure to welcome Michael Filler, Associate Professor and the Traylor Faculty Fellow in the School of Chemical and Biomolecular Engineering at Georgia Tech. Michael, thank you so much for joining us today. To get us started, can you tell us a little bit about yourself and how you first got involved in nanotechnology?
Sure. Thanks for having me. It's a real pleasure to be here. I'm excited to share a bit about what we do in the lab. I'm a chemical engineer by training. So chemical engineers think about how we produce products, most often molecules and chemicals, but not always, on a massive scale. And with that scale comes dramatic reductions in cost. So much of the things that are around you were enabled by chemical engineers, from the clothing you're wearing, right, to the paint on the wall and things like that. That was kind of where I got trained as an undergrad. And as a PhD student, I worked on the surfaces of semiconductors. Pauli once said that God made the bulk and surfaces were invented by the devil. It's one of my favorite quotes. And so when you break the bonds with atoms neighboring each other in the bulk of a material and expose a surface, atoms do all sorts of weird, funky things, and they rearrange, and they're very sensitive to their environment and all sorts of stuff. So we studied this for semiconductor surfaces, and that turns out to be really important in a lot of electronic devices. And so understanding those behaviors is important for improving chips and other sorts of things. And then after that work, my postdoc, that's where I kind of got my feet wet building functional devices. So at Caltech, I built nano and micro wire-based solar cells. So a lot of what we do today in the lab is kind of a combination of all three of those things, thinking about what happens at massive manufacturing scale, leveraging surfaces, understanding surfaces, and then building devices.
So from a chemical engineering point of view, can you talk a little bit about the process you use to make nanowires, and then maybe some details about why you would want to use them to make functional devices?
I think one of the things that we think about a lot, maybe sets us apart from some other labs, is the intersection of function and manufacturing scale. So in manufacturing, you don't just get everything for free. So you have to make trade-offs between how good is it going to function and how large of a scale can you produce it at. That's an important thing to keep in mind. We work a lot with nanowires, as you mentioned. So nanowires are exactly what they sound like. They're one-dimensional objects that are, microns in length and tens of nanometers in diameter. And one of the most important aspects of them is how we grow them and what you can create along their length. So we grow them in this process known as the VLS, or vapor liquid solid process. So you have to imagine a little tiny catalytic droplet sitting on top of the growing nanowire. And that droplet accepts atoms from the vapor phase. It concentrates them and then precipitates them into new semiconductor layers in the nanowire. So what happens in that little tiny droplet's a lot like sugar precipitating out of water, except it's semiconductor atoms precipitating out of a molten metal to form that wire. And you can add different materials at different times. And so what this allows you to do is program composition. So say you're growing a wire that's for a transistor, and it's a silicon wire, and you flow with that silicon some phosphorus to grow one of the source or the drain, and then you change from phosphorus to boron to grow the channel, and then you turn it back off and turn phosphorus back on to grow the other side of the device. And so you can create these exquisitely compositionally controlled materials through this process. And to me, not only is it nano, but it's a programmability with the process that is really powerful. So what do you do with this? And that is, you build functional things. So I mentioned transistors. And getting back to this question about the intersection between functionality and scale, we would really like to be able to make buckets of gigahertz transistors. So how do you make bulk quantities of devices that are, from a performance perspective, pretty similar to what's in chips today, but at a throughput and a cost that's a lot more like molecules? And then you get to ask the fun questions like, what do you do with that? What does it change about the world that we live in today? What new things become possible that aren't possible? And so that's a lot of what we think about.
So one of the things I understand you're interested in and what might be possible is on-demand electronics. Can you describe that concept and how what you're doing applies to that?
So there's a lot of folks out there who have built on-demand platforms for circuit boards and things like that. But in terms of in terms of basically building circuits that are like chips in an on-demand fashion, we don't have that technology, right? So our modern fabs are billions of dollars. The non-recurring engineering costs are often hundreds of thousands, if not millions of dollars. The lead times are many months. What we're talking about are platforms that would allow you to make circuitry that performs like modern chips. It would be different circuitry, but performs at a level like modern chips, but you could do it in your garage. You could do it in the lab. You could do it on a space station. And so what are those applications? What are those use cases? So for example, think about bioelectronics. There's a lot of interesting work going on in prosthetics, and everyone's anatomy is different at different points in time and because of their own bodies. And so thinking about how you would customize electronic interfaces for biology is a really interesting use case of this kind of technology, at least in the early days. Other use cases might be in cryptography, where you really want a bunch of super unique circuits. Actually, it's a problem if all the circuits are identical. You want them to be unique, intentionally unique. I think that will open up new opportunities in physical cryptography for tracking parts or other things related to that.
How do you reconcile, an individual wire to turning that into an actual device that's connected to micro and bulk scale?
Right. First of all, when I say device, I tend to refer to the nanoelectronic device. The transistor, I call the device, and then the circuit is the collection of devices that are interconnected. So how do you do that? So two things. I want to point out that a lot of nanowire work has been on the nanowire part and not on bottom-up building the rest of the device. So that's part one. We can make these exquisite nanowires, but they're still not devices, right? A transistor has a gate stack, it has source drain contacts, and we don't have really great processes for fabricating those on top of the wire in a scalable manner. And so we've done some work developing new patterning processes that would allow us to do that, which I think is part one. Part two is now I have my bucket of transistors. How do I make a functional circuit? And I think a really important thing to think about is to step back from assuming we need perfection in placement of devices and in the devices themselves even, but really in placement. We tend to think, because of the amazing pictures we see that come out of the semiconductor industry, that perfection is required, and I disagree with that sentiment. And so we're developing ways to, for example, put down devices, and inherent in our process is the assumption that they are not perfectly placed. And how do you go find them? How do you figure out where they are and then connect to them to build a functional circuit? And so we're actually using some AI and machine learning kinds of algorithms to figure out how to make circuitry from imperfectly placed devices. And I kind of expect the future of these kinds of things, they'll look more like brains. We see these pictures of neurons in the brain and we think, oh, that's amazing. And then we see pictures of perfectly aligned transistors and interconnects and ICs. We think that's amazing too. I think these kinds of on-demand electronic circuits will look more like neurons in the brain than the perfectly ordered things we fab today. But there's a long way to go between here and there.
So a long way to go. What are your projections? What does the timeline look like?
That's a great question. I hope we have prototypes in the next 5 years kind of thing. Developing all of the systems and tools that you need to do it at scale and do it cost effectively and reliably, right? We all know that takes longer. But I would hope in a 10 to 20 year time frame, this is a kind of technology that starts to make it out of the lab and into startups.
Have you engaged also in areas of energy harvesting and other applications, these forests of nanowires and thermal gradients, vibration collection, and any of those types of applications?
Yes, my postdoc work was in solar cells. That's still maybe an interesting space, maybe to marry it with silicon that's already made industrially, of course, at a pretty massive scale. Other kinds of spaces that I've worked in, heat transport is one of them. We've done some work building these plasmonic resonators in wires. So the programmability of the wire allows you to put in these little doped regions. And if you string them along and put them at just the right spacing from each other, they couple to each other. And so you can heat one end, excite this resonator. It's like a spring, basically. And then it connects with the neighboring resonator because it's attached. And it just kind of progresses down the chain. And so that might be a new way to control how we transport heat in solids. So things like that we've done some work on in the past. Our push has been into electronics. It's interesting. You look at electronics and you think, that's really complicated, so why do that? And I think that's been the mindset of a lot of people. At the same time, like the solar cell stuff is maybe even harder. It looks simple. It looks like it's just a diode. It's just this one simple device. But when you do it out of nanomaterials and you need every nanowire, if you're doing it out of nanowires, to be oriented exactly the right position out of trillions of wires, or many more, honestly, and one is backwards, that's now a short. And so there's a lot of kind of seemingly silly practical challenges to making what in aggregate is a simple device out of nanomaterials. And I think it's important to appreciate, though, that nanowires are opening up these avenues of application that just were entirely off limits before.
So I want to switch gears a little bit. Can you talk a little bit about what tools you need for your work and how you see the future accessibility of these tools, the impact that can have on the research community and development community?
I mean, it's absolutely essential, right? Without these kinds of tools, all the work I was describing of nanowire synthesis, device synthesis, circuit fab, we wouldn't be able to do the prototyping work. And that's what's essential to prove it's not impossible. Right? I can hand wave all day and show you PowerPoint slides, but of course, until you do the work, no one really believes you. So that infrastructure is central to it. I'll point out, a lot of our work at the same time, we think about how do we democratize this? And so while we're doing prototyping in the NNCI facilities, we are also thinking about, I want this on someone's desk. I want them to be able to do this themselves and find out what the applications are because the barrier to entry is really low. It's a $1,000 printer of electronic systems versus, millions of dollars of fab equipment. But you got to start somewhere. And like I said, it's absolutely essential. I think I'd have a hard time doing a lot of the work we do in other places.
And what types of tools do you use? Do you use scanning probe microscopy, transmission electron microscopy? Can you share a little bit more about the characterization that you do?
Sure. I mean, characterization is central and remains challenging for nanomaterials. Like we've made such progress in the last 20 years, but it's still hard. So transmission electron microscopy. So looking at the composition of these different parts of the transistor as we make it, or after we've made it, we want to see what we made or thought we made, usually. And it's exquisite, the resolution of these instruments. You can see the placement of atoms. You can see what the atoms are in many cases. One of the challenges that we face all the time is, well, what is it in a distribution of nanowires or a distribution of devices you've built? How similar are devices to each other? That's actually really important knowledge. We do a lot of surface analysis. So a lot of the fabrication steps that we've developed in the lab to build that complete transistor are surface dependent. We rely on surfaces to do them. And so needing to do things like X-ray photoelectron spectroscopy, doing AFM sometimes, those kinds of things are also central to enabling what we're trying to do.
Can you talk about your perspective on interdisciplinarity and the makeup of your lab, your students and postdocs?
For sure. I mean, this is my favorite part of the work, is working with other people who have distinct backgrounds from mine. I joke with my material science colleagues that materials aren't everything. And so I push back all the time on the value of process innovation, and that there's usually a yin and a yang between a material that can be made versus its properties. And so we talk about that a lot. But I work with, at the colleague level, I have obviously chemical engineers I work with, mechanical engineers. When you're doing printing of interconnect lines with additive manufacturing techniques, right? We need mechanical engineers who tend to be really good at that. Obviously, electrical engineers. I work with people on human-computer interaction. So, what do you do with this thing once you've made it, right? Thinking about those kinds of cases. Design, how do you design a product? And public policy, right? If everyone could print integrated circuits in their garage, what does that mean for policies, both before and after it's possible? And these folks have just taught me so much. And so I think that's essential. In the lab, we're a little bit more focused, right? It's important to be not a jack of all trades and master of none, right? So we obviously a bunch of chemical engineers, material scientists, and electrical engineers in the lab.
And do you have undergrads in your lab?
I certainly do. They tend to do stuff outside of the clean room, mostly from a cost perspective, but we increasingly do have plenty of things we don't do in the clean room. A lot of the patterning steps can be done in a glove box and things like that. So they'll work on things like that. Probably 30% of my lab is undergrads at this point.
Do you have advice that you share with them or perhaps with high school students that might be interested in research or a career in nanoscience or nanotechnology?
So in terms of nano, couple things. So nano's a kind of a weird discipline in that it's a little bit like math, right? It's both its own sort of discipline and it's also enabling of many other disciplines. Kind of unlike math, though, it hasn't yet found its, a core canon. I mean, I think we could write some stuff down, but I think it's hard if you're going, particularly for an undergraduate degree, into a nano degree. My suggestion would be to choose a more traditional discipline, something with a really deep core that we know is broadly applicable in lots of problems, and then apply it to problems in nano or use nano to fix or solve problems in that discipline, particularly at the undergraduate level. I think it's different at the graduate level once you've been trained in a foundational topic. Again, you don't want to be a jack of all trades, master of none kind of thing.
So, Michael, thank you so much for taking the time to talk with us today and telling us your story from the NNI. Do you have any closing thoughts that you'd like to share with our listeners?
So this is not so much nano. This is just kind of career advice I wish I had gotten. Have confidence in yourself that other people aren't any smarter than you are. They just have 20 years more experience on what they're working on. And, one of the interesting things about doing something new that no one's worked on is no one has any experience in it. So I think that's important to try and appreciate. But I recognize it can be hard when you're starting out. And finally, learn something about business strategy and how to tell compelling stories. I don't think we do this enough in STEM. Train students to think about strategy. I mean, we teach them how to solve problems, but how do you convince others this problem is worth solving? What is the business case, for example? Not all business, but what is the technology case for this, right? And learn to tell a story around it. Humans are storytellers. And so in my experience, finding better ways to tell my story, for example, about on-demand electronics has been really powerful.